Okay, so we're going to talk a little bit about bare metal Kubernetes, okay, mixed architectures. Question: how many of you guys are running Kubernetes on public clouds? Okay. This was just to see if you were paying attention. How many of you are running it on bare metal? Okay, cool. Right. So this is great, you know, because this type of conferences, I always ask this sort of questions, and usually everybody runs Kubernetes on top of public clouds, but then I see increasing number of hands at every event of people running it on their own environment. What would be the advantages? Well, the primary reason to run on bare metal is performance, right? You have the hardware. If you use it only for that, why not, right? Usually we as a company, Cloudbase, when we talk about Kubernetes with our customers, the options are typically two. It's either OpenStack with on top Magnum, ideally with a new cluster API plugin, right? Not the hit one. And running on top of a traditional infrastructure as a service, or going directly bare metal, you know? And the answer very often from the customer is, you know, we have still a lot of VMs, we have a lot of traditional workloads, we want to run them side by side, and we prefer to still have the majority of the workload running in VMs, and then we have an increasing amount of containers coming up, right? So this is, of course, shifting over time. Now we have more and more people coming in and saying, hey, you know what, most of my workloads are at this point containerized, you know, so I don't really need VMs anymore. And for the limited number of VMs they might have, at this point we have also Kubevirt, you know, embedded in the system, so you don't need to have any more a full-fledged infrastructure service for that. You have access to everything, so especially nowadays there is a lot of work around AI, right? You want to have your GPUs, you want to your GPUs to share directly with your containers, so you don't want to have a middle layers with VM again for nothing, right? Security-wise, of course, there is a lot to discuss here. There are projects like, you know, Kata containers, Flatcar, you know, that allow you, of course, to use virtualization primitives, not to go too much into details right now, to have a decent degree of separation between workloads, right, while retaining the advantage of running containers. But if you are the only tenant, or you're the company, if you want, that shares the same security boundary, then you can also go with traditional, simple, you know, containers. It's great, of course, for your own private cloud, you know, nothing against hyperscalers. So we work with hyperscalers, we like them, I think it's great. But if you have heavy workloads, you know, your bill will start, you know, getting big very, very quickly. So it makes a lot of sense to have your own hardware and run your own infrastructure on premise. Then, of course, you have scenarios where for either governmental situations or banks or stuff like that, you cannot simply have anything outside. You need to have, of course, air-gapped environment, and it has to be everything entirely local, you know. Those are all perfectly good reasons for running your own bare metal infrastructure. Or better said, your own on-premise infrastructure for which you might evaluate the bare metal use case. Cons: somebody drops servers on your doorstep, and then you have to figure out how to handle everything from there, right? So hard to automate. So coming from an OpenStack background, we have a long history in automating, you know, from the bare metal up. So adding a new layer with Kubernetes was relatively natural, you know, but if you come from a DevOps background and are used to just deploy VMs on top of hyperscalers and gone from there, that's another layer you have to learn. Hardware can be a mix and match, you know. Ideally, you have all the servers identical. Reality is usually a lot of different things. So you have to deal with the complexity of the potential complexity of a lot of different hardware. Okay, reproducibility issues, right? You know, you might have, you know, scenarios in which you want to reproduce a specific bug that happens on your environment and is specific to the hardware that you use. Might be hard to get your vendor to help you out with that. And then security, of course, if your nodes have access directly to the hardware, there we enter a completely different discussion, okay? It's achievable, it's great, right? But you have additional complexity layer, while hyperscalers or clouds like OpenStack will hide that complexity from you. On top of that, we are also adding mixed architecture. So we have customers like Ampere Computing, for example, that work with ARM CPUs, and we have more and more customers that are coming in having that as a requirement for a variety of reasons. To begin with, any of you guys using ARM servers? Cool, great. This is actually getting more and more interesting because, of course, it gives you a lot of advantages in terms of computational aspects, right? It allows you to run different type of workloads, and a lot of the type of things that people containerize are really platform agnostic. So it really doesn't matter if they run on an X64 or an ARM64. ARM64 CPUs are also very mature, and so also are the chips, the SoCs offered by most of the companies. Okay. You can mix and match them, meaning that you can keep x64, for situations in which, you have legacy containers. I mean, assuming the legacy containers are a thing. You have anyway legacy workloads which simply don't work for a reason or another on ARM64, and you can keep both of them in the same Kubernetes deployments, like simply separating them by the type of image and scheduling rows. On the con side, you have, of course, not all the container images are available for both platforms, so that's one problem. And some of the features might not yet be up to speed on ARM. Typically everything comes first for x64, and then it catches up on the ARM side. Okay, I will pass it to my colleague Adi to go on with infrastructure and run a demo.
Hello, thank you for your intro, Alessandro. So now let's get to the real part on the actually how to deploy this Kubernetes on bare metal. Currently, we have here a solution that has it's specifically made for where you have a management cluster which has everything inside the Kubernetes, and you want to deploy another Kubernetes cluster or more. So you need first a management node where you install a management Kubernetes cluster where you put all the middleware to basically deploy the workload clusters. So you can deploy one workload clusters, multiple workload clusters, maybe different between them or the same. So in the management cluster, it's heavily relying on the cluster API. So cluster API is a set of services that you manage the lifecycle of the workload cluster. The nice part with the cluster API is that sometimes you have deployed your workload cluster, and then you can basically plug it off, or plug it in when you need to scale down, scale up your workload cluster. On the left-hand side, on the management cluster, so cluster API is the core of it. ArgoCD enables us to make the logical partitions of the applications that we want to install. So the workload cluster, it's in itself an app of apps or a set of apps in ArgoCD. Of course, you also need a remote repository, a Git repository. And for the part that handles all the bare metal lifecycle, we use Tinkerbell. Tinkerbell, it's an open source tool created initially by Packet, now Equinix Metal. On the workload cluster, we want to install everything that is required. So what do we require? We require CNI, a container network interface, with Cilium, a container storage interface with Ceph in this case. You can have also Longhorn. Of course, instead of Cilium, you can have Calico. And then you can also put Kubevirt. In the live demo that I'll start right now, we will have also some validation applications, which are, again, an Argo application set. For example, WordPress that uses Ceph as a as PVC storage backend, virtual machines, and more. Let me start the deployment. Question. Can you see the screen? So now I already have a very small deployment with 2 VMs. This is a virtualized environment because we are time constrained. So it should take around 15 minutes. Hopefully, this thing will work. Okay, going back to the architecture sky-high view. So the management Kubernetes cluster, it manages the lifecycle of the workload cluster. Everything is Kubernetes. In the management cluster, you have the required stuff for the bare metal. In this case, Pixie server, a BMC manager, a workload cluster manager. Of course, it can be an image server, Docker registry, Git repository if you have air-gapped scenarios. Okay. For the management cluster, a recap, I already had an Ubuntu 22.04 installed. To initialize the management cluster Kubernetes, we've chosen K3D for the, I will let you know in a moment what were the motives behind that. ArgoCD, Tinkerbell from, again, and of course we'll have the observability stack with Prometheus, Grafana, and Sentry. The management cluster, it should be quite heavy from the CPU count, RAM count, especially if you put Prometheus and Grafana. So you need quite a lot of cores to handle that. The workload cluster. So we would like for Tinkerbell, actually cluster API via Tinkerbell, to install a Flatcar container Linux as a base OS for the cluster. Then it will install Cilium, and then Ceph, Kubevirt, and then you can do validation by checking various applications and VMs. You can also have Azure Arc enabled, and there are some hardware constraints, like especially L2 network connectivity between the workload cluster nodes, or basically management node, and workload cluster nodes, because that's how Pixie works. So let's get started with each part of the management Kubernetes cluster. So we tried a lot to see what's the best way to actually initialize the egg, the management cluster. The best way was to have K3D. It's K3S on Docker, which allows you to basically do 100% reproducible builds for the management cluster. Because you just remove the Docker container and all your cluster is gone. Nothing happened to actually the host environment. So it's the cleanest way we could find. Of course, it has to be, the load balancer has to be disabled because the packets, the L2 packets, need to get to that Kubernetes cluster. So you cannot have L3, L4 load balancer. It's the DHCP options that are used for the Pixie boot. Okay, ArgoCD, everyone knows ArgoCD. In this case, it's great to have the app of apps pattern, so you can isolate logically from the management cluster to the workload cluster, and then to the actual applications that you want to install on the management cluster and workload cluster. So it's great to have this logical, let's say, split. Then, of course, it's a declarative, reproducible automation. So once you can run it twice, it should be idempotent at any time, should be. There was a presentation earlier on by the CTC, and you can have drift. They also talked about that. Everything is in a Git repo, so definitely you need to have some sort of secret vault. So we chose to have a Bitnami sealed secrets. So basically you have just one master key that you keep outside of the Git repository, and then every credential is encrypted at rest on the Git repository. This is It's a small thing, but is a very crucial thing for the stuff. Then Kubevip and everything needed, because I said no load balancer. Then Tinkerbell. Tinkerbell, as I said, it's a packet open source. Packet open sourced it at the moment. It's automation for bare metal. So how it works? You have several services in the management cluster Kubernetes, and then you have Rufio for the BMC, Pixie for boots. One small detail: when it boots, when the workload cluster node boots, it does not boot directly Flatcar. It boots Linux kit-based OS, which basically then gets the workflows from Tinkerbell, and workflows instruct the worker from the hook OS to do something like, okay, take this Flatcar image, put it on dev VDA1 or VDA on the storage, create the bonds, create VLANs if you need it during the Pixie boot. And then you can also manage the Flatcar partitions if you want. Maybe put something in those. One other note about HookOS, it needs to have all the network and storage drivers. So basically, at the moment, we had to basically recompile the Linux kernel used by HookOS to enable some special servers that were not supported. Then the core of the things is Cluster API. Who here has used Cluster API? So this is very, let's say, has tons of functionality. It can run as a backend for OpenStack, for Amazon, for Amazon EC2, for Google Cloud, and more. And the link between Tinkerbell and the Cluster API is the Cluster API provider for Tinkerbell, Capt, which is also provided as open source, was open sourced by Packet. One note here: when Cluster API needs an image that has been already installed with everything that Kubernetes needs, kubeadmin, kubectl, and more. So you need to have special images for that. Flatcar Container OS, on the other side, you can basically take the production image from the release page, and then you can specify at initrd, at early boot, okay, take this Kubernetes version. And basically, Flatcar, because it's a read-only container OS, this Kubernetes, let's say, version, it's in itself a partition or raw disk, which has a file system, which is, again, read-only, and it overlays on it. Oh, sorry. That one is working. That one is not working. Sorry for that. Maybe. Yeah, let's. So, once ArgoCD, Tinkerbell, and Cluster API has been already installed on the management cluster, you have a simple, let's say, an appliance image that you can basically take and move it when we're on the customer premises where you want to install that. That can speed up and make air-gap deployments way faster and possible. Okay, let's go to the workload cluster installation. So you have these three are all ArgoCD apps. So the first app, the hardware app, creates the CRD entities for Tinkerbell to know how to manage the nodes. So basically, you need for each node, you need one such hardware CRD entity. The machine Argo application holds all the data to manage, to Pixie boot the servers, to start them, to stop them, to do a one-shot Pixie boot, for example. And then the workload cluster is the actual definition, it's a YAML definition of how the workload cluster should look like. What OS should have there, how it should be, how many replicas for how many control planes, how many replicas for how many worker nodes, and in addition is bare metal for mixed architectures. You can have multiple machine instances, one for AMD64, one for ARM64. So basically, you can plug and play how many replicas your workload cluster should look like, and then when you sync the workload cluster, you should have this in the ArgoCD interface. Let me check for a moment. So it got to quite further in the. Let me see if I can get to the. Okay, so the demo is working nicely, at least this part. Okay, so here is our ArgoCD UI. So if I go here to the labels, these are the management apps. For the sake of the speed of the demo, I have not installed the Prometheus and monitoring. It takes quite a while, more than 5 minutes. And I also haven't installed Bird. We'll get that in a moment. So you see here the machine. The Think stack is for Tinkerbell. Workload apps is the seed for the actual workload labs apps, meaning Cilium and Ceph. And the workload cluster, it's here already, so it's already synced. Let me get some nodes. So yes, we have 4 minutes ago. For the live demo, I chose the latest and greatest Kubernetes version 130. It works perfectly. Yesterday, I was running 128.5. So it's just one change, because Flatcar makes it really easy to change. It's just one line change, and it will take the Kubernetes version, the new Kubernetes version. Okay. I'll let Alessandro know.
A few choices from the architectural standpoint. How many of you guys use Cilium already? Okay, cool. How many of you use Calico? Okay. So we come from an OpenStack background, so our original choice was to use an OpenStack-based technology for this particular project as well. But we found out that we could take advantage of eBPF, since it got very mature as a technology, right? It's fantastic for sandboxing a lot of kernel level type of tooling, right? Including Cilium, which is based on eBPF and allows you to basically have a CNI, which is perfectly working for our particular bare metal scenario. It has, of course, some things you have to take into account. For example, it has a BGP mode. It needs Bird, as we talked like recently, as a drop-in BGP peer, if there is no switch support. A2 announcement mode, which is also very easy to use, which is very nice. Yeah, and if you want, you can just put in Calico if you'd like, or any other CNI for the sake of it. I think we'll get to that later. Another interesting choice is the storage side of things. I mean, we like typically hyperconverged architectures, right? They're not mandatory, but this is something that could allow you to basically have nodes that take care of both compute and storage at the same time, which is not a bad idea if your hardware allows that. Or if you prefer, of course, you can have a completely separate storage pool somewhere else, right? Ceph, of course, it's another one of those projects we are actively involved with, like OpenStack and Kubernetes. We are the company who ported it to Windows after all, so we are very well vested in that community as well. So we decided to use it and optimize it for this particular use case as well. Not everyone thinks that Ceph is the perfect solution for Kubernetes. For example, famously, SUSE decided to go with Locron with that. But with proper optimization, proper number of nodes, it's a great solution. Okay, I think that's enough. Storage can be afterwards consumed by pods using PVCs. Of course, that's like any other storage solution in Kubernetes, right? Can be very resource intensive, like that goes without saying. That's part, of course, how Ceph works. That's relatively independent from the Kubernetes use case. Last but not least, we talked about VMs, right? So the idea here is to be able to have also VMs running over here, is what in Romanian is called a struzzo Camilla, right?
But it's bare metal, so it makes sense. It makes sense.
But it allows you to enable a lot of cases where replatforming is very difficult, right? So it becomes really easy at that point to take your VMs, move them, and migrate them basically, and let them run in your environment as well. It also provides, virtualization primitives. After all, it's based on KVM and QEMU, right? So you have also security in terms of the same type of security we'll expect for that. One of the big advantages is that you share, of course, the same networking namespaces and whatnot with your containers. So it's quite different than having your VMs on one side and the containers on the other. Plus, you have a single management pane on top of it. Well, networking can be, of course, a bit problematic. The multi-CNI, it's useful in that case, right? Okay, floating IPs, you assign them with the load balancing IPs. And the provisioning, of course, you do it typically with config drive, right? Which means that you can use Cloudbase init or Cloudbase init if you use Windows to do that. Oh, and well, by the way, you can also do Linux or Windows VMs in this case, which is not a bad thing to have. ARM64 managed to catch up, so we have also Kubevirt working on ARM64 with some limitations, in particular the fact that you don't support CPU hot plug. Okay, back to Adi.
Thank you. So let's see what happened to our deployment. Okay, still waiting for something, but meanwhile we can definitely go here in the ArgoCD and go to the workload apps. So here is our workload apps, everything that is running on the cluster, the workload cluster that has just been provisioned. It takes around 12 to 15 minutes to do this whole workflow on a good VM, especially for this demo. So here you have the Kubevirt, and then we have some Nginx to test a Rook Ceph cluster operator. Let me go here a bit. Okay, 16 minutes. That's good. Okay, what I want to do is this, to check if Ceph is running fine. So it's running fine. We have one OSD that it's happily going. Let's do now a get service -a. So these are floating IPs or load balancer IPs, and I was interested in this IP. So the test VM ArgoCD app should have created a VM. So literally I can do this, and yeah, it should work. Well, I need to, so it responds. I have a VNC viewer here that should work, so here it is. Let me do a Fedora, and uptime, so it should up 2 minutes ago. Great. Let's see, does it have internet? Probably yes. It also has internet, perfect. So getting back to, so the CNI, CSI, Kubevirt works fine.
I think we are at the limit with the time. The demo finished, that was our goal, right? Present the architecture and everything, and get one working. The demo gods were kind with us today. So we have everything. I think we can go directly to the Q&A part.
Sure.
Okay. Because we have 1 minute. Those are resources. Everything is open source. We call the project BMK. You can find a lot of information here, including a list of blog posts that we published on the Cloudbase website. If you have any questions, okay, beside now, of course, you can reach out to us either here at the conference or via email or open source channels in general, right? Okay, questions?
Hello, I have two questions. First and foremost, I'm a little bit confused because you mentioned bare metal, but at the same time, I've seen some virtualizations. So I expected some shared kernel stuff. So this is confusing a little bit for me.
Yeah, this is the demo. The demo was...
He exposed our trick.
So the demo was done because the bare metal would have taken 35 minutes at least, so I couldn't do it. But I have here a real environment with 3 nodes, 1 worker node AMD64, 1 worker node ARM, and 1 control plane on ARM. For example, I have 3 VMs actually, 1 on AMD64 and 2 on ARM64. And to show you that I'm not
lying.
So this is how it looks like. But this one, for example, 2 nodes. So how cluster API works is like first control plane, and then it starts the other ones. So if I had 2 nodes, it would have made it, not even the virtual one would have made it into 30 minutes.
Yeah, the main problem is that when you boot the machines, right, it takes like a bunch of minutes.
It takes at least 5 to 4 minutes to actually boot a bare metal versus nothing. On the virtual machine.
If you have time, you can repeat the whole thing. Right?
Yeah, I would be glad to if you have 40 minutes.
And another small one, you are not using a service mesh in your entire architecture. You're implementing by yourself all the service discovery, mutual TLS stuff.
Well, that's on top of it. It's something that it's part of the workloads that you might want to run on top of it. We don't need service meshes for the infrastructure itself.
Yeah, you can put afterwards Linkerd or HT or yeah, it has already Cilium, which is great for all as a base layer.
Cool, thank you.
I think we have time for a couple of more questions.
Okay.
So you mentioned in your architecture that you're using Flatcar for your OS. I know there's a popularity growing with all of these container-specific operating systems. Are there any specific reasons you went with Flatcar compared to other OS choices?
I can respond and answer to that. The first thing is that we are part of the community.
I'm a maintainer.
Yeah, Adi is a maintainer, and we found it as a perfect balance, let's say, between traditional operating systems and the modern, of course, completely. Let's say, solution without any ephemeral storage, right? We are also maintainers, as we mentioned, so we can also take care of CVEs, all security aspects, and take care of the whole pipeline from the OS upwards, so that's a huge advantage. Flatcar is basically the old core OS that became Flatcar with Kinvolk, and then now after the acquisition from Kinvolk by Microsoft, it's being incubated, it's about to be incubated in as part of the CNCF Foundation.
One small comment on that. You can basically, with Flatcar and systemd sysxt, because I used it for Kubernetes, you can upgrade, roll over the Flatcar independently from the Kubernetes. So you can upgrade Kubernetes differently from the Flatcar. So and it gives you great flexibility, and also, Flatcar has A/B partitions, and
so the upgrade story is very important in this. Unfortunately, we don't have the time to cover it, but happy to discuss it later.
You have it here, how you can change Kubernetes and roll it out automatically or not. For example, this is the magic part that if now it's 130.0, if Flatcar builds 130.1, it will automatically update. I have my nodes already to have those updates.
One more question?
Because you're using Ceph, when you provision with PXE, do you wipe all the disk or you leave the disks to be reused?
You are required, if you have Ceph already installed before or something is on those disks, you have to clean them, wipe them out. Yeah, Ceph won't install on the unclean devices. Yes. Yeah. So basically, Tinkerbell can have steps. So one step is getting the Flatcar put on /dev/ and then the other next step, you can basically instruct it to DD wipe, DD0 the devices that are not the boot devices, or especially you can make policies. It's very so this is cluster API stuff. So it's very flexible, and with the Tinkerbell workflows.
That's about all the time that we have. Thank you so much.
Thank you very much. Mulțumim.